Hey there guys, how's it going? This is Mike coming back at you here with another video on number theory. In the previous video, we saw several samples of solving linear congruences. In this video, we are going to learn how do we solve a system of linear congruences. Things where we have two unknowns, x and y, and we have two equations to solve. So what these systems of linear congruences look like is just like what you see on your screen here. Something of the form ax plus by is congruent to p mod n, as well as cx plus dy is congruent to q mod n. And what we are going to look at with these is when does a system like this have a solution? Is there more than one distinct solution to a system of linear congruences? And then if we have a solution, how do we find it? So what we're going to first see, we'll tackle two of these questions in one. So if we have this system, ax plus by is congruent to p mod n, and cx plus dy is congruent to q mod n, this system has a unique solution when the GCD of AD minus BC and n is equal to 1. So we are never going to come up with more than one solution. We're always going to come up with a single solution. And a single solution consists of something for x and something for y. Those two things combined make your one solution. And the condition that has to hold in order for us to have this unique solution, you have to do a times d minus b times c. You'll get some number, take the GCD of that number and your n value, and if those two things are relatively prime, then you know that there is a unique solution. Doing AD minus BC, that's a lot like doing the determinant of a 2x2 matrix. For those of us who like to think of things in a linear algebra perspective. So this tells us when we have a solution and how many we have. How do we go about finding the solution? Well, we're really going to go through the process with a sample problem, but I'll just say beforehand that solving a system of linear congruences is very similar to solving a system of linear equations, like you would do back in 8th grade or just entering high school. Both processes begin the same, but then they differ slightly halfway through. So we're going to go through this method of solving these systems of linear congruences, I should say. We're going to go through this process with a sample problem here. So this is our system that we're going to solve. 4x plus 5y is congruent to 8 mod 9, and 2x plus 6y is congruent to 3 mod 9. First thing we have to check, does the GCD of AD minus BC and my n value equal 1? So first we need to calculate a times d minus b times c. So we have 4 times 6, which is 24, minus 5 times 2, which is 10. 24 minus 10 is 14. And yes, the GCD of 14 and 9 is indeed 1. So we do have a unique solution to this given system of linear congruences. Now, I said that the process to solving this system starts off the same way as you would typically solve a system of linear equations. That is true. We're going to kick it off by eliminating one of our variables. We're going to multiply each congruence by an appropriate constant so that we can remove one of x or y, and then we will subtract one from the other. That's what will actually clear out the x or the y. Then we have a single linear congruence in terms of the remaining variable, which we can then solve. So, as I just said, we begin by multiplying each congruence by an appropriate factor to eliminate one variable. For this particular problem, I'm going to multiply the entire first congruence here by 6, and then the second one by 5, and I'm going to subtract the 2. By doing this, I'm going to get rid of my y's, and I'll just have x's left. So when I do that, I'm going to have 24x minus 10x, which is 14x, but I'm taking this mod 9, and 14 mod 9 is 5. So that gets me my 5x. I'm going to have 6 times 8, which is 48, minus 5 times 3, or 15. 48 minus 15 is 33, and take that mod 9, you get 6. So I'm down to the single linear congruence. 5x is congruent to 6 mod 9. It's really pretty straightforward here to solve for x. If I multiply both sides of this guy by 2, I get 10x, which taken mod 9, it just gives me 1x, or x, is congruent to 12, but 12 mod 9 is 3. So x is congruent to 3 mod 9. So I found one of my unknown values. I found the value for my x. Now I need to find my y value. And this is where things differ just a little bit. When you would typically hit this point in solving a system of linear equations, you'd be tempted to substitute your x value back in, and you would then subtract things over, and you could then add the two equations and solve for your x value, and that would be valid. But we're not going to do that here. You do not want to substitute your one known value back in when solving a linear congruence. It's not guaranteed to lead you to the correct value for your other variable. Instead, we're just going to do the same operation that we did for the first half of it. We're just going to eliminate the other variable now, and we're going to solve for y. So I'm going to go back just a bit here. I'm going to, I need to clear out the x's now. So to do that, if I just multiply the second equation by a minus 2, and then add those, or multiply the second equation by 2 and then subtract those, you would come up with 5y minus 12y, which is negative 7y. Now this leaves us at a little bit of an interesting point, because so far up until now we haven't really done, or we haven't really seen any problems here where we have numbers that are less than 0 showing up in these congruences. If you arrive at a point where you have a negative coefficient or a negative number showing up, you simply change that to a positive number that is congruent to the number that you had. So typically we're subtracting 9s from numbers to get it down to something smaller. In this case, I'm going to add 9s until I get a positive whole number that's less than 9. Negative 7 is congruent to 2 mod 9. I just added 1 9 onto the negative 7. So negative 7y is congruent to 2y. And then I had 8 minus 6, or 2. So now I have 2y is congruent to 2 mod 9. And it's really straightforward here to see that y is congruent to 1. So now we have our unique solution to this given system of linear congruences. X is congruent to 3, and y is congruent to 1. And what you could do is you could take these values, 3 for x and y for 1, and substitute them into your given system of equations, system of linear congruences here, and check to see that it does indeed hold. 3 for x, 1 for y. That's going to make this first guy 17. Take 17 mod 9, and you get 8. This is going to be 2 times 3, which is 6. This is going to be 6 times 1, which is 6. 6 plus 6 is 12. Take 12 mod 9, and you get 3. So that's your final check there, just to see that we do indeed have a valid x and y value for our solution. So that's the method that we use for solving these systems of linear congruences. You're just eliminating one variable in 2 separate cases. You're going to get rid of one variable, solve for the other one, then going back to the given system of congruences, you're going to then eliminate the variable that you just found a value for, and then solve for the other variable, the one that you don't have any value for yet. So here's another one that we will go through. Solve this system. 8x plus 9y is congruent to 14 mod 16, and 3x plus 5y is congruent to 1 mod 16. And we want to solve this system here. Again, first thing we have to do, find a times d minus b times c, and then take the GCD of that number and our n value, and make sure that that GCD is 1. Well, if you do that, 8 times 5 is 40, 9 times 3 is 27, 40 minus 27 is 13, GCD of 13 and 16 is 1, so we're good. I'm going to first eliminate my x's and solve for y. So I'm going to multiply the first congruence here by a 3 and multiply the second congruence by an 8, and then I'm going to take the difference. So when I do that, I am going to have, this will become a 27y, and this will become a 40y. So I'll have 27y minus 40y, which is negative 13y, but negative 13 is congruent to 3 mod 16. So negative 13y is congruent to 3y. And then if I take the 14, multiply it by a 3, that gives me 42. Take the 8, multiply it by the 1, gives me 8. 42 minus 8 is 34. And 34 is congruent to 2 mod 16. So now I'm down to solving this nicer linear congruence. 3y is congruent to 2 mod 16. You have to multiply by a little bit of a larger number, but it's not too bad. If you multiply both sides by 11, you get 33y, which is congruent to y, because 33 is congruent to 1 mod 16. And then 2 times 11 is 22. Take that mod 16, that gives you 6. So y is congruent to 6 here. So that's one of my values which I am looking for. I'm now going to go back to the given system. I now need to clear out my y's and solve for x's. So to do that, I'm going to multiply the first one here by 5, and then I'm going to multiply the second guy here by 9. So when I do that, that is going to give me 8x times 5, or 40x, minus 9 times 3x, or minus 27x, and this will give me positive 13x. The constants, 5 times 14 is 70, minus 9 times 1 is 9. So 70 minus 9 is 61, but taken mod 16, that is 13. So we are down to 13x is congruent to 13 mod 16. Pretty straightforward here to see that x is congruent to 1 is going to be the value that you are looking for. So we found our unique solution to this particular problem here. X is congruent to 1 and Y is congruent to 6. You can check, substitute each of these values into the given system, and you will get both linear congruences to hold. So this one here, I want you to try this guy on your own, see if you can find the unique solution to it. Yes, 7 times 7 is 49, 4 times 2 is 8, 49 minus 8 is 41, 41 and 11 are relatively prime to each other, so we do have a unique solution. But go through the process that we've gone through in these two previous problems. Try to come up with the answer on your own. So press pause here. Try to solve this problem. Once you think you have once you have completed it and you think you have the correct answer, press play, and we'll see if you were correct. Okay, let's see if you guys came up with the correct value for X and the correct value for Y. First, I eliminated the X's, so I'm multiplying the top congruence by 4 and the bottom one by 7. I have 4 times the 2y gives me 8y, 7 times the 7y gives me 49y. 8y minus 49y gives me the negative 41y, but mod 11, negative 41 is congruent to 3. So negative 41y is congruent to 3y. And then I have the 4 times the 10, which is 40, minus the 7 times the 5, which is 35, and 40 minus 35 is 5. So I'm down to the linear congruence 3y is congruent to 5, mod 11. If you multiply both sides by 4 and simplify, you find that y is congruent to 9. Now, I'm going to eliminate the y's and solve for x, which means I'm going to multiply the first congruence by 7, and then multiply the second congruence by 2. 7 times the 7x gives me 49x, 2 times the 4x gives me 8x, 49x minus 8x is positive 41x, but 41 mod 11 is 8. So that's why we have the 8x there. I have the 7 times the 10 to give me 70, minus the 2 times the 5 to give me 10. 70 minus 10 is 60. 60 mod 11 is 5. So I'm solving 8x is congruent to 5 mod 11. This is now a little bit trickier. There's no nice, clear, low number that I can multiply 8 by and then take that product mod 11 and come up with ideally 1. But if I take 8 and multiply it by 3 and then take that product, which is 24, take that mod 11, it gets me down to 2. So 24x, which is congruent to 2x mod 11, is congruent to 15, but 15 mod 11 is 4. So I have 2x is congruent to 4 mod 11, or x is congruent to 2. So there is our solution. Y is congruent to 9, and x is congruent to 2. So that is our unique solution. So this is how we solve systems of linear congruences. Things where we have x's and y's, and they're congruent to things mod the same whole number, mod the same value of n. This section was not necessarily inside of our notes, so if you like to refer back to the textbook, there is something in the textbook on there, but otherwise, outside of using other internet resources, this is all of the information provided on this one particular topic. In the next video, we're going to talk about a very important theorem in number theory. It's called the Chinese remainder theorem, and we're going to see how we solve systems of linear congruences, but these ones don't contain two variables, x and y. They just contain one. But the other difference is that the n value is not the same in every one of our congruences that we have inside of that system. So you'll see in the next video what those things look like and how do we deal with those kinds of things. If you have any questions or comments, be sure to drop them in the comments section below. Otherwise, until the next video, take it easy, guys.